Hi everyone, today we're going to be talking about equations that involve fractional exponents, which really just is finishing up our radical equations because we know another representation of radicals is fractional exponent. In order to solve these problems, we're going to follow these basic guideline steps for the most part. We want to isolate the term raised to the fractional exponent, similar to isolating the radical from the last lesson. We're going to raise each side of the equation to the reciprocal of the fractional exponent to force an exponent of 1. It is what you were doing in the last lesson. We just didn't change to our fractional exponent form before raising both sides to the whatever. This time you're going to have fractional exponents to raise, and these exponents, a lot of them will have a numerator and a denominator. That is not 1. You want to simplify your radical notation. You should be able to do this without a calculator. I'm going to show you the easiest way to do it by hand, and then you just solve the equation and check for extraneous solutions. You know that you're not allowed to have negative numbers under even radicals, so that's really when we get into our extraneous solution situations. When you're solving, you're going to be dealing with mostly linear or quadratic equations. They are going to be equations that you know how to solve by hand. You should be able to do this entire lesson without a calculator. There is one extra step though. If the numerator of the original exponent is even, you have to apply absolute value to that side of the equation, the one that falls out of the radical or the fractional exponent, when raising both sides to reciprocal. We do have to account for the fact that when we raise something to an even power, if it's negative, it'll be positive, and if it's positive, it'll be positive. So the absolute value allows us to find both solutions or all solutions to these fractional exponent problems. The reason we didn't have to worry about this in our last lesson is because if you're dealing with a cube root or a fourth root, the fractional exponent notation to that is 1/4. We're caring about this numerator, and here our numerator is odd. So it's only going to have one option for an answer. If it's even, then we're raising it to an even power. We have to worry about our negatives. So here's our first example. Similar to our last set of equations in this unit, we are going to isolate the radical or the fractional exponent and divide by 2. This part should be a part that you're comfortable with, resulting in this equation. Now to undo an exponent of 4/5, I notice that 4/5, this 4 numerator is even in the original, which is a big deal. That implies absolute value. We need it. So this side, when I raise to the reciprocal to get that 1, the x minus 1 is going to fall into absolute values. And then I'm solving an absolute value equation. So we have to rely on our prior knowledge. When I raise this side to the 5/4, that's just radical notation. That is going to become the 4th root of something raised to the 5th. So I'm going to fill in the rest of the equation. That x minus 1 is what falls out of the radical because it has an exponent of 1 now. The equal sign stays there. And 16 will be inside of our radical here. I intentionally chose this notation where the 5 is on the outside of the parentheses because I know the 4th root of 16 is 2. I don't really know what 16 to the power of 5 would be. So it'd be really hard for me to, take that power and then take a 4th root of it all in my head. But I can figure out that 2 to the 5th is 32, simplifying that side of the equation. So my absolute value equation is x minus 1, and absolute value is equal to 32. I know from solving absolute value equations that in order to solve this, I need to isolate my absolute value, which is already done for me. I have the equation I see, and the equation, the absolute value inside, never changes, is equal to the opposite of the other side. So the opposite of 32 is negative 32, giving me x values of positive 33 and negative 31. I'm not finished though. I do have to check these answers, so I'm going to go back and substitute into the original problem. You do have to show a written check like I am doing here if x is equal to 33. Well, this notation is not great. Again, I'm going to use the radical notation with the power on the outside so that I could do it in my head. So 2 times 16 plus 4. 2 times 16 is 32 plus 4 is 36. I'm comfortable where I could say 33 is definitely a solution to my equation. I also need to check x equals negative 31. Again, using the radical notation with the power on the outside so I can do it in my head. A fifth root of negative 32, the negative is allowed to come out of a fifth root, and it comes out as a negative because the fifth root is odd. The fifth root of 32 is 2, so that's actually 2 times negative 2 to the fourth. And 2 times 16 plus 4, we're at the same place we were before, which is nice because it is 36, leading me to say that these are both solutions to my problem. All right, so let's look at an example like number 2. Here we have two different fractional exponents that would represent two different radicals. We kind of want to follow the same process and isolate one of the radicals. So the easiest thing I see to do here is to add this term to both sides, isolating both radicals in this case. Rewriting my equation to be x plus 5 to the 1/2 is equal to 5 minus 2x to the 1/4. When you're presented with this situation, you want to make sure that both sides have integer exponents because it's a lot easier to work with equations that have integer exponents rather than fractional exponents. So I want to look at a common denominator and raise both sides to that common denominator, eliminating the fraction. I notice here that 2 and 4 both have a common denominator of 4. So if I raise both sides to the 4th, my equation will become x plus 5 squared is equal to 5 minus 2x to the first power. Both integers, both powers I know how to work with. I don't have to worry about absolute value because both of the numerators in the original equation are odd. So on my left-hand side, this x plus 5 squared, I do have to FOIL that. Something raised to the first power is just itself, so that right-hand side could stay the same. This is a quadratic equation. The most efficient way to solve a quadratic equation is set it equal to 0 and factor, giving me possible x solutions of negative 10 and negative 2. I say possible solutions because I do need to go back to my original equation and check both of these values, trying to catch extraneous solutions here. When I substitute in negative 10, I get negative 5 raised to the 1/2. I know that 1/2 exponent is a representation of a square root, and I also know that the radicand of a square root cannot be negative. So right away, I realized that negative 10 is an extraneous solution to this problem. It's not possible. Cannot have a negative even root. So I actually don't need to do any more of that check. I have to follow through with the other x value. I want that to be equal to 0. I don't know if this is 0 yet, but I do know that 9 can be rewritten as 3 squared. And I can apply my power of a power property here and rewrite this term as 3 to the 1/2. So if I subtract 3 to the 1/2 by itself, 3 to the 1/2, that is equal to 0, proving that x equals negative 2 is a solution to this equation. So my final answer would be x equals negative 2.